be talking on an equivariant main conjecture in Iwasawa theory. Yeah.
Again, thank you. Thank you for thinking till the very last talk. So what I'm gonna do today is I'll talk about Iwasawa theory again. There were several talks about Iwasawa theory here. Mine is not going to be non-commutative today, but this can be made non-commutative. I'm sorry to disappoint you. Yeah. So, and in the process, I'm going to review a few things that were discussed in the previous lectures by Samit and Mahesh and Dominic as well. Yeah. Unlike Dominic, who denoted Zelmer for Nabla, my Zelmer will be the real Zelmer. So Nabla is not going to show up. There won't be any confusion. Okay. All right. So this is joint work with my former student, Rusiru Gambira, who is now a postdoc at UC Santa Barbara, working with BC Akbula and Francesca Stea. So I will start with some motivation. I mean, what motivated us to look into this equivariant main conjecture in Iwasawa theory that you are going to see at the very end of the lecture. So the motivation goes back to my work with Cornelius Greiter. So Cornelius and I, about 14, 15 years ago, started thinking very seriously about proving Brummer-Stark. But our strategy was very different from that of Mahesh and Samit. We wanted to prove Brummer-Stark by simply proving an equivariant main conjecture in Iwasawa theory using Wiles's work. So we would start at the top of the Iwasawa tower, prove something equivariant up there, and then do co-descent down the Iwasawa tower and get strong Brummer-Stark that way. You will see that we got a form of strong Brummer-Stark, but it's an imprimitive form. Okay, so it's quite unsatisfactory from some point of view. And we had to make some assumptions along the way. So this is called, this is why I call this a conditional equivariant main conjecture. So let me just describe my work with Greiter and what followed from that. And then I will move on to describe an unconditional equivariant main conjecture and how that relates to what I proved with Greiter. And then I'll draw some conclusions. I'll give you some additional applications which were not discussed in the conference at all. So what is the setup? So the setup is very similar to what Yuka was describing in her talk. So except for the fact that I want to make things equivariant, G equivariant, so I start with a Galois extension of a CM number field capital K over a totally real number field F. The Galois group is abelian and it's denoted by G. I'm going to fix a prime number. So in this talk, I'm going to stay away from 2. I will make some comments at the end about the prime 2, which is more difficult. So I fix a prime p greater than 2, and I'm going to assume for simplicity that the pth roots of unity are in the top field capital K. Therefore, the cyclotomic ZP extension of capital K, which I denote by K infinity, is simply obtained from capital K by adjoining all the p power roots of unity. Yeah, and I denote by gamma the Galois group of this cyclotomic ZP extension of capital K. Gamma is isomorphic to ZP as a topological group, as you know. I will denote by script G this Galois group of K infinity all the way down to F. Yeah. The nth layer in the cyclotomic extension is denoted by Kn. And the Galois group of the nth layer over F is denoted by Gn. And now I'm going to start playing the games that Mahesh and Samit are playing. So I'm going to fix 2 sets of primes, S and T, 2 finite disjoint sets of non-Archimedean primes in the base field F. And here, since I'm going up the Iwasawa tower, which is ramified at all the p-adic primes, I'm going to assume that S contains the p-adic primes in F, which is denoted by the set of those is denoted by SP of F. Okay. And now here is an Iwasawa module that Greiter and I looked at. So I'm going to, at the top of the Iwasawa tower, so I'm taking the S integers at the top of the Iwasawa tower, OK infinity S. So I get this scheme, this affine scheme, spectrum of OK infinity S. And I'm going to take the closed immersion of the points, the set of points sitting above the points in T in K infinity. So this is finite. It's a closed subset inside the spectrum of OK infinity S. I'm going to denote by JT this closed immersion. And I am going to consider the following et al. Cohomology group with compact supports. So it's H1 et al. On the spectrum of OK infinity S of the sheaf JT lower shriek of QP mod ZP twisted once, a la Tate. The twists are Tate twists here. So they are twists by powers of the cyclotomic character. So due to the fact that S and T live inside F, and when you lift them to K infinity, they give you G invariant sets of points. Okay, this module acquires naturally a structure of a ZP double bracket script G module. Okay, so this is the equivariant Iwasawa algebra I'm talking about. Why is it equivariant? Because there is this action of this little g at the bottom. It's not only gamma, it's the whole script G, which has a quotient equal to this little g at the bottom. And I'm going to take the minus eigenspace. Everything will happen on the minus side. So I'm mudding out by 1 plus complex conjugation. This is what's happening. So this is the minus eigenspace. Now, this module is hard to swallow. You will see a better definition, much more palatable definition in a little bit. But for the moment, let me give you some facts about this module. So what is its structure as a ZP module? Well, it turns out that it's a bunch of copies, finitely many copies of QP mod ZP. So the number of copies is lambda here, which depends on T and S. This is a generalization of the classical lambda invariant in Iwasawa theory. And plus, so a direct sum with a ZP module of finite exponent P to the mu. This mu is the classical mu invariant in Iwasawa theory. As you know, Iwasawa conjectured that mu is equal to 0 in this very general context. So that is the same as saying, if you look at this structure theorem, that is the same as saying that this module M of K infinity minus is a divisible module. So in other words, this ZP module of finite exponent P to the mu is trivial. Okay. And we are going to take the Pontryagin dual of this thing. So these are homomorphisms over ZP of this module with coefficients in QP mod ZP. And this becomes all of a sudden a finitely generated torsion ZP double bracket G minus module. Okay, so this is a true Iwasawa module. It's something compact. Okay. These are the modules that Iwasawa theory deals with. So Yuka gave you a structure theory. In the case where script G is gamma, script G is not gamma now. It's a little bit more complicated. So there is no structure theory over these equivariant rings as easy to state as it was in Yuka's talk. Okay, why look at this module? So in previous work with Greiter, we looked at a similar situation in the case where K and F are global fields of positive characteristics. So this is the geometric situation. These are fields of rational functions on smooth projective curves over a finite field. And the extension K over F corresponds to a Galois cover of such curves. So this is the geometric situation. So K and F are function fields, global fields of positive characteristic. And to this data in that geometric situation, one can associate what's called a Picard-1 motive, which I denote here by Pic sub S upper T. So this is a geometric object. It was introduced by Dulin in the 1970s in his mixed Hodge structure papers, third paper in that series, if you are interested to look at it. And roughly speaking, what it consists of, it's a semi-abelian variety, which means it's an extension of an abelian variety by a torus. The abelian variety floating about is one of the Jacobians of these curves that I'm talking about. And some extra data. The extra data comes from S, the torus comes from T, and so forth. I'm not going to get into details. But whenever you have a one motive, a Picard one motive, you can talk about its P to the n torsion for every single P. And it turns out that this M that I discussed previously, this et al. Cohomology group with compact supports, it's nothing else but the P infinity torsion of this Picard one motive. And as a consequence, the Pontryagin dual becomes nothing else but the p-adic realization, the p-adic Tate module, TP of this Picard one motive, dual, ZP dual. Okay, so this has geometric meaning to me, okay? So in this work in 2008, studying this geometric situation, Greiter and I were interested in understanding the ZP double bracket G module structure of this TP of peak TS star, and proved the following equivariant main conjecture in that geometric setting. So we proved that the projective dimension of this TP of MST star over the equivariant Iwasawa algebra is 1. Okay, and we computed the fitting ideal over ZP. So this is fit 0. Yeah, so these are the only fitting ideals that were discussed in this conference. There are higher fitting ideals that are also meaningful, but we haven't discussed those. So this is the ones that one of the ones that we discussed. So fit 0 of this TP of the Picard motive star is generated by a certain equivariant p-adical function. So it's principal generated by a certain equivariant p-adical. This is exactly what you want out of an equivariant main conjecture in this context. So this was the geometric context. And we wanted to create a situation like this in the arithmetic case, in the case of number fields, and that's what that module that I showed you before, this H1 et al. With compact supports does, in fact. Why were we interested in this equivariant main conjecture? Because, as I said, I mean, I was interested in proving Brumer-Stark, and we proved strong Brumer-Stark in the geometric setting. And in addition, we proved what is called the strong Cotes-Sinnott conjecture. So these were not discussed here in this conference, but I'll touch upon them at the very end of this lecture. They are very important conjectures about special values of L functions at negative integers. Yeah, not at 0. Brumer-Stark is about values at 0. Okay, so this is a completely satisfactory picture in the geometric setting, yeah, in the function field setting, and we wanted to make it work in the number field setting as well. Okay, so let's forget the modules for the moment. Let me tell you what the L functions are. So this is a review of what you saw in the previous lectures. So for simplicity, for the moment, I'm going to assume that this set S contains the ramification locus of K infinity over F. In particular, it contains the p-adic primes, because K infinity over K is ramified at all the p-adic primes. And I'm going to assume that T is non-empty, and remember S and T are disjoint. Okay, so these are the usual hypotheses you are assuming on S and T. And as you saw in the previous lectures, to this data, you can associate a G equivariant L function, theta sub S upper T, associated to S and T and the extension K over F. And it's defined on C, but it takes values in the group ring, C bracket G. It's analytic everywhere. And if you are looking at it for the real part of S greater than 1, it's an infinite Euler product which looks like this. So it's a product over all the primes nuttiness. I'm looking at the second part of the product, 1 minus sigma V inverse times the normal V to the minus S to the minus 1. So that's the usual equivariant Euler product. And then you adjust it. You smooth it out with some Euler factors at the primes in T. And they look like this, 1 minus sigma V inverse normal V to the 1 minus S. You only saw these Euler factors at S equals 0. Yeah, I'm giving you the full Euler factors. So for the real part of S greater than 1, this converges absolutely and uniformly on compact subsets. And then you extend it by analyticity. It's analytic. You would have a pole somewhere, but the pole at S equals 1 and the trivial character chi equals the identity, but that pole is taken care of by these Euler factors at T, okay? And so this is the integrality resolved by Pierret, Cassuno-Guess, and Dulin and Ribet. They proved it independently and with different methods. That was discussed before. I'm discussing it at all integers, all negative integers. So theta at 1 minus n for all n greater than or equal to 1 integer. We knew from work of Klingen and Siegel that this is an element in Q bracket G. And what Pierret, Cassuno-Guess, and Dulin and Ribet proved is that, in fact, under this hypothesis, it's p-adically integral. So it's in the intersection Q bracket G intersection ZP bracket G. We are interested in p-adically integral special values of L functions. And now, what do you do? So in order to deal with the main conjecture I'm talking about, you have to push these elements to the top of the Iwasawa tower. So what you do, you take their values at 0 at each finite layer in the cyclotomic ZP extension. So you are looking at these values, theta associated to Kn over F at 0. And it turns out that they are compatible with respect to the projection maps at the level of group rings. And you take the projective limit, and all of a sudden you arrive at this theta associated to K infinity over F, which lives in the minus part of the Iwasawa algebra. This was discussed. These special values die if you evaluate them against even characters. Yeah, due to the fact that, there are infinite primes in the totally real field downstairs, which split in the maximal totally real sub-extension of this K over F. Okay, so you end up in the right Iwasawa algebra in ZP double bracket G minus. Okay, I have to make a remark here. So I did make these hypotheses. These are quite strong hypotheses on S and T, but these integrality results hold under weaker hypothesis on S and T, and that's why, so I'm not going to mention the weaker hypothesis in detail in what follows, but if you see some S and T which do not satisfy these properties, and I'm still claiming that the function is integral, I mean, these elements theta are integral, that is due to an observation, a key remark of Kurihara, okay? All right, so let me just explain what my result with Greiter was in the number field case. So it's a conditional equivariant main conjecture. Why is it conditional? Because we had to assume for technical reasons, serious technical reasons, this was not a frivolous assumption that could be removed with a little bit more work, that the Iwasawa mu invariant conjecture holds. In other words, we assume that mu is equal to 0. And the usual assumptions on S and T. And then we prove that in the number field case, just as it is the case in the function field case, the dual of this module, so M dual, is a ZP double bracket G minus module, which is quadratically presented and of projective dimension 1 over this Iwasawa algebra. Remember the definition of quadratically presented from, so this means that there is a presentation of the type ring to the n going into ring to the n, same n going into the module. That implies right away that the fitting ideal is principal, The fitting ideal is simply generated by the determinant of this of the matrix. Yeah, and the main conjecture simply says here, and this is what we prove, that the fitting ideal of the over this Iwasawa algebra of this module is generated by this theta at the k infinity level that I just defined, this projective limit. So this is an equivariant p-adical function. It satisfies p-adic interpolation properties, relating it to values of the global L functions at negative integers. Yeah, but it is equivariant. It lives in the equivariant Iwasawa algebra. All right, so this is the corollary. Remember, we were after Brumer-Stark. Okay, so here is what we could prove at the time about Brumer-Stark. So theta at 0 at the finite level, k over f, is in the fitting ideal over ZP bracket G. So we are taking it one prime at a time, and I fix the prime P, and my P is greater than 2. So I'm looking at the P primary part of the T ideal class group. So this is the T ray class group of the ideal class group in the T ray class group of the top field capital. Okay, so it's in the fitting ideal of the dual of this P primary part of the T ray class group. So this would be clean Brumer-Stark, and everything would be fine, and we would have been done then. Two things, two caveats. Mu equals 0. I did say that this is an assumption. We don't know how to prove this unless the extensions in question are abelian over Q. So this is a theorem of Ferrero and Washington. These are the only instances where we can prove that mu is equal to 0. Everybody believes that mu is equal to 0, but this is beyond of what we can prove right now. And there is one other thing. I am assuming, so in clean Brumer-Stark, you have to assume that the ramification locus of K over F is inside S, not the ramification locus of K infinity over F. So what's the difference? I am forcing in some p-adic primes in S, which may not be ramified in K over F. These ramified primes, these p-adic primes that may not be unramified in K over F, could cause this L value, this theta at 0, to vanish. So for example, if one of these primes, which is not ramified in K over F, splits in K over F, the left-hand side is dead. So you are killing the special value. So this is why this is called an imprimitive Brumer-Stark conjecture. Okay, that's why we were not, this was the state of knowledge on Brumer-Stark at the time, and it was not really Brumer-Stark, it was imprimitive Brumer-Stark. Imprimitivity was eliminated under certain strong hypotheses, which pretty much implied that the ideal class group in question is cohomologically trivial over G, via the method of Taylor-Wiles primes, and beyond that, we couldn't do any. Yeah, so this was all we could do. But then we proved a clean, strong code-synod conjecture, so I can tell you now what that is. So that is about the values of this function at 1 minus n, okay? And for n greater than or equal to 2 now, so I'm looking at negative integers. We haven't discussed that in this. What are they related to? I mean, what replaces the ideal class group? And what replaces the ideal class group are the Quillen K groups of OKS, the even Quillen K groups of OKS. I'll discuss these things a little later in detail. How do you integralize it? Well, you hit it with the fitting ideal over ZP bracket G of the torsion part of the odd Quillen K group, P primary part of the odd Quillen K group of OKS. And you are getting almost the entire fitting ideal. You have to cut it out by an idempotent, which idempotent is either plus or minus, depending on whether n is even or odd. When you move to negative integers, these special values could live on the plus side, depending on the parity of n. Yeah, plus or minus side. That's why you are not getting the whole fitting ideal. You are only getting a piece of the fitting ideal. Coates and Synod had conjectured that you land in the annihilation of k sub 2n minus 2. This is much stronger. So this is strong Coates Synod. There is no imprimitivity here. The imprimitivity doesn't matter because if you throw in additional primes, p-adic primes, and you compute the Euler factors at negative integers, those are invertible in the group ring. So you can just get rid of them. They can never kill the L function. Yeah. So this is a clean cosinus, but it's still conditional in the sense that mu is equal to 0. Yeah. All right. So our methods were purely Iwasawa theoretic. So we took Wiles's 1990 proof of the main conjecture for classical Iwasawa modules over totally real number fields. And we made it into something equivariant. So what we did is we replaced the classical Iwasawa modules with these new ones, these H1 et al.'s with compact supports, which satisfied better cohomological properties. They were of projective dimension 1 over the Iwasawa algebra, and that's how we proved it. If you want to recover Wiles's result from this, you simply tensor it with Q. So it's a non-integral. Wiles's result is a non-integral version of this. So that was it. And my motivation with my student, Rusiru, was, so we wanted to eliminate the hypothesis mu equals 0 from these statements. I mean, that's, yeah. Imprimitivity, as far as Brummer-Stark was concerned, I mean, we were aware that we couldn't, but luckily Brummer-Stark was proved in the meantime. So we wanted to take advantage of that. So this is where the Zellmer modules of Burns, Kurihara, and Sano show up. So what's happening here is the following. So I'm going to review a few definitions that you've seen before. Okay, I think this is not going to hurt anything. And then I will relate these Zellmer groups that you saw before to these Iwasawa modules that Greiter and I were considering. Okay. So here is what happens. So I'll have a K over F, P, S, and T as above. I'm not imposing any conditions on S and T for the moment. I just want S and T to be disjoint from one another. And they can be empty for all I care for this slide. Okay, so no conditions here. So you denote by KT cross the elements in K cross which are congruent to one modulo every single prime in T. And you consider a certain divisor map from KT cross to the divisors of K supported away from S union T. Okay, so this is the divisor map. And the co-kernel of this divisor map is the T ideal class group mod out by the classes generated by the primes in S. So this is a quotient of the T ideal class group. It's the ST ideal class group that shows up all over the place in Dasgupta and Kadu. Okay. Now you apply the dual functor, the Z dual functor, which I denote by star here, and you take the co-kernel. Oh, sorry. You take the co-kernel of the dual of the divisor map, and that's your Zellmer group. This is Zellmer S upper T that showed up in Samit's and Mahesh's lectures. One more time, this Zellmer showed up in Dominic's lecture just a few minutes ago, but in fact, this is a different one. Okay, yeah. So his is Nabla, and this is true Zellmer. Okay. All right. So this is endowed with a Z bracket G module structure. Yeah, and I want to make a real simple observation. So if you work out the details, you will see that there is a short exact sequence of ZP bracket G modules, yeah, where the minus part of this Zellmer group is, of the P primary part of this Zellmer group is in the middle. It projects upon the dual of the T ideal class group, the full T ideal class group, okay? And in the kernel, you have the duals of the S divisors of capital K, tensored with ZP and taking the minus part. This is an exact sequence, okay? It's quite elementary to prove that this is an exact sequence, but this is a crucial piece of information because, for example, if you know the fitting ideal of this guy, since it projects upon the ideal class group, the T ideal class group, you will know that the fitting ideal of the Zelmer is inside the fitting ideal of the T ideal class group, the dual of the T ideal class group. Extremely important. Okay. So here is what Dasgupta and Kagde, based on earlier work of Ritter Weiss, I have to say, and based on even earlier work of John Tate, the fundamental paper that goes into this is, the first fundamental paper that goes into this is John Tate's paper published in the 1960s in a Japanese journal, maybe Tohoku, maybe something else. And the title of the paper is Cohomology of Tori. Okay, so what do Dasgupta and Kagde prove based on this earlier work of Ritter, Weiss, and Tate? So they prove that if the p-ramified primes for K over F are in S, and the ramification locus, the entire ramification locus for K over S is in S union T, then this p primary part of the Zelmer group, the Zelmer module, has a quadratic presentation, okay, which looks like B going into, in their work was V, I'm using this fancy V, going into Zelmer, where B and V, they depend on a different set S prime. I'll say a little bit about this set S prime of primes. So they are free modules of rank cardinality of S prime minus 1. What is this S prime? Is a large enough set of finite set of primes in F, but large enough to contain S, to be disjoint from T, and satisfy some technical conditions. I mean, one of the technical conditions is that the primes in S prime generate the T ideal class group. But there is one other condition. So these all come from work of Ritter and Weiss and earlier work of Tate. Okay. So one comment here, in general, this ZP bracket G module, this Zelmer module that we are interested in studying for reasons related to the previous exact sequence, has infinite projective dimension. So this means that it's not Galois cohomologically trivial. It's not G cohomologically trivial. Yeah. However, since it is quadratically presented, its fitting ideal is principal. And now here is a conjecture of Burns, Kurihara, and Sano that was mentioned here many times. So if the P ramification locus is in S and the entire ramification locus is in S union T, plus an extra condition which simply says that there are no P power roots of unity which are congruent to one modulo all the primes in T which are unramified in K over F. This is very important. Then the fitting ideal of this Zelmer module, Zelmer group, I'm sorry, the P primary part of the Zelmer group and the minus part is generated by the special value of this L function, global L function, theta at 0. So this is an instance. I mentioned that S and T do not satisfy the standard condition. S contains the entire ramification locus and T satisfies some other conditions. So these are not satisfied here, but it falls under this remark of Kurihara's, which ensures that this theta is actually integral under these conditions I am imposing on it. So this was the Burns, Kurihara, and Sano conjecture. And of course, I mean, as I mentioned before, so it's from the previous exact sequence, I mean, if you know that your theta is in the Zelmer group of this guy, is in the fitting ideal of the Zelmer group, then theta is going to be in the fitting ideal of the T ideal class group dual, and that's strong Brummer star. So clearly, Burns, Kurihara, and Sano implies strong Brummer star. Okay, at primes P greater than 2. I mean, I'm not discussing the 2 primary part. By the way, nobody said it here, but for the 2 primary part, so if you were to replace here P by 2, this is a false statement. Theta is not in the fitting ideal of the dual of the ideal class group. It's just in the annihilator. You get some bonus. You can divide theta by a power of 2, and you still end up with something integral. And but you only end up in the annihilator. We've known counterexamples to theta being in the fitting ideal of the dual of the two primary part of this ideal class group for a long time. Yeah. So annihilator. Yeah. Brumer and Stark only conjecture things about annihilators to begin with. Okay. So yeah. So that's why these are called strong Brumer-Stark, right? You end up in an ideal which is smaller than the annihilator, this fitting ideal. Yeah. All right. So here is what we started. So by the way, this work was happening in 2021. So the state of knowledge at that time was Dasgupta and Kagde's original paper on Brumer-Stark. And so the keystone result was the following. If S consists exactly of the P ramified primes in K over F, and the ramification locus is inside S union T, plus this technical condition on P torsion, then the fitting ideal of the Zellmer is generated by the special value of the L function. So this is a little weaker than Burns-Kurihara-Asano because of this extremely strong condition on S. Okay, so remember in Burns-Kurihara-Asano, S has to contain SP ramified over K. However, Dasgupta and Kagde in this paper, their paper on Brumer-Stark, where they prove Brumer-Stark for P greater than 2, show that this is still strong enough, not only via that exact sequence, that exact sequence is not going to take care of things. It's still strong enough to prove strong Brumer-Stark. Okay, so what we did, we started with this keystone result, and we managed to prove Burns-Kurihara-Asano. So there are several proofs now of Burns-Kurihara-Asano. We proved Burns-Kurihara-Asano with our own methods. So I'm just going to tell you how we did it. So first of all, we established some canonical morphisms between the quadratic presentations of the Zellmer modules in question. Remember, they are quadratically presented in finite extensions. Okay, so what if you have a quadratic presentation for this extension and you have a quadratic presentation for this extension? Can you relate them? And somehow you can relate them canonically, and that relation, so something like this was mentioned in Samit's last talk yesterday, actually. So we related them, and that relation allowed us to prove a certain codescent properties for these Zellmer modules. And this codescent property combined with the keystone result of Dasgupta and Kagde allowed us to prove a P primitive version of Burns-Kurihara-Asano. What do I mean by P primitive? You already know what that means now. I'm imposing the following condition on S: the entire P primary part, P primary locus of F is inside S. All the p-adic primes are inside S, not only the ramified ones. And now we proceeded to remove the imprimitivity. Remember, I had tried to remove the imprimitivity with Greiter from our result on Brumer-Stark, and we could, under some strong cohomological triviality assumptions on the ideal class group. Here we managed to remove imprimitivity using the Taylor-Wiles method. And it's funny, I mean, these Zellmer groups are not cohomologically trivial. So the method should not have worked, but the fact that they are quadratically presented allowed us to adjust the method a little bit, and we removed imprimitivity, and that's our proof. It's just a few pages of Burns-Kurihara-Asano. I have to confess, so yesterday, Dasgupta mentioned a way of proving the ETNC minus based on ideas of Kurihara, again, relating quadratic presentations of these Zellmer groups at different levels. Our method takes care of ETNC minus 2 as well, not at 2, at P greater than 2. I don't know how to do it. But ETNC minus is not going to show up in this talk. This is good enough for us. So Burns-Kurihara-Asano is good enough. So of course, I have to mention this work that was mentioned several times. So there are other proofs of Burns-Kurihara-Sano. There are other proofs of ETNC minus, which implies Burns-Kurihara-Sano. So one is due to Burns, Bulak, Daoud, and Seo, and Dominic mentioned their method. I mean, it has something to do with the rigidity of Euler systems. And another one by Dasgupta Kagde, and that was pushed to P equals 2 as well. So, yeah. Our proof can be read by a beginning graduate student in a few hours. Okay, so how do we go to the Iwasawa Tower now? So I have to go back to my original goal, the main conjecture. So I'm gonna take my set of data. I'm going to assume that the p-adic primes are in S, and I'm going to assume that T contains some unramified primes. And I will assume, as usual, that S ramified for K infinity over F is inside S union T. And now I'll climb up the Iwasawa Tower. So at each level in the Iwasawa Tower, I have a Zellmer group for this data, minus part P primary part. And there are restriction maps. And these restriction maps are surjective. And I take the projective limit and I get the Zellmer group. So this is the Zellmer group at the top of the Iwasawa Tower. The definition is projective limit of the Zellmer groups at the finite levels, minus part P primary part. This acquires a ZP bracket, double bracket G minus module structure, yeah? And so it's a module over the Iwasawa algebra. And here is what you can prove. This is what Rusiro and I proved in 2022, that this module at the top of the Iwasawa Tower, unlike the ones at the finite levels, has projective dimension 1 over the group ring. So it is in particular cohomologically trivial. Those were not. And it is, of course, quadratically presented. Yeah. And that we have an equality of ideals inside ZP double bracket G minus fitting of this guy. The Zellmer group at the very top is generated by the p-adical function. Yeah, the equivariant p-adical function. This is the shape of an equivariant main conjecture for this particular module, the Zellmer module. And, you know, the sketch of the proof is the following. So you use Burns-Kurihara-Sano at each finite level. So you have an equality of fitting of Zellmer at the level n is equal to the special value of the L function at level n. And you take a projective limit. There is a theorem of Kurihara and Greiter which allows you to take projective limits. And you are going to get equality 2 from that. Yeah, not 1. You are not getting anything about cohomological triviality. But then you prove that this theta of K infinity over F is a non-zero divisor in the Iwasawa algebra. Okay, so there is some work there. And that implies right away number 1. It implies quadratic presentation and finite projective dimension. Projective dimension 1. Okay? If it is finite, it has to be 1 over these rings. Rings have rule dimension 2. Yeah. Anyway, I have to say that a similar equivariant main conjecture was proved with different methods by Henri Johnston and Andreas Nickel. Yeah, so you can see their paper. It was published, and you can compare. And now, what happened to my module with Greiter? I mean, what happened to this Picard-1 motive module? That was my primary goal. And here is the link between my work with Greiter that happened 14, 15 years ago and this new work on Zellmer modules. Well, it turns out that this Zellmer module at the top of the Iwasawa Tower and the Picard-1 motive type module that Greiter and I looked at, so this H1 et al. With compact supports, are endowed with a duality pairing, with a perfect duality pairing. Going into QP mod ZP, we construct the pairing explicitly. And therefore Zelmer is nothing else but the Pontryagin dual of the module I was considering with Greiter. Okay. So if I have the fitting ideal with of Zelmer, this is the main conjecture. I have the fitting ideal of the module I was considering with Greiter. Yeah, M dual. So this is the main conjecture now, the reformulation of the equivariant main conjecture in the terms that Greiter and I were thinking of 14, 15 years ago. And this ties up these Zelmer groups, if you want, with these Picard-1 motives that Dulin constructed in the function field setting a long time ago, which Greiter and I considered when we discussed, when we tried to prove and proved equivariant main conjectures in the geometric setting. Okay. So this is it. This is what the equivariant main conjecture is. What are the conditions on S and T? So SP of F is inside T. So these are the p-adic primes. They have to be all there because when you go up the Iwasawa tower, they are all ramified. And you want T to contain some unramified primes, and you want S union T to contain the entire ramification locus of K infinity. Then this module is stratified, and the projective dimension is 1, and its fitting ideal is exactly the equivariant p-adical function. Okay? So this relates work done 15 years ago with work done by Samit Dasgupta and Mahesh Kagde, and with this new formulation of the main conjecture in terms of these Zelmer groups, the Burns-Kurihara-Sano Zelmer groups. Let me give you an application. Okay, an application not towards Brumer-Stark. I mean, that's done. Let me give you an application towards Cotes-Sinnott. So remember, Greiter and I had proved Cotes-Sinnott conditionally under mu equals 0. Now, there is no mu equals 0 done anymore, assumed anymore. So this is an unconditional result. Does it imply anything about Cotes-Sinnott? So let me tell you a little bit about these Quillen K groups, because they were never discussed in this conference, and they are the replacements for the ideal class group when you look at special values of L functions, equivariant or not, at negative integers. Okay, so they have. So I'm going to start with a K over F as before, with an S and a P. I'm not going to discuss T here. T doesn't play a role in what follows. I'm going to assume that P is greater than 2. I'll discuss P equals 2 in a bit. And I'm going to assume that the ramification locus of K infinity over F is inside S. So in particular, the p-adic primes are inside S. So what is the ith K group, Ki? These are the Quillen K groups of OKS. Well, the definition is a little technical. So this is Quillen's definition. Okay, he got a Fields Medal for this stuff. So you take a certain classifying space of the general linear group over OKS with entries in OKS. You modify it a little bit. This is the plus construction of Quillen. You add, so this is a topological space. You add some 2 cells, some 3 cells cleverly. You modify it a little bit. You arrive at a topological space, which is this BGL plus. And then you take the ith homotopy group. That's it. This is Ki. You can define it like this for any ring, but let's stick with this. For all I greater than or equal to 0. So this is Quillen's definition, 1970s. Okay. What are the properties of these Quillen K groups? In the case where the ring is OKS, I mean the ring of S integers of a number field. So I'm looking at the even ones and the odd ones. They have completely different behavior. So let's look at K sub 2n of OKS for n greater than or equal to 1, and K sub 2n minus 1 of OKS for n greater than or equal to 1 for the moment. I'm going to look at n equals 0 in a moment. So the even one is always finite, and the odd one is finitely generated. If you are wondering what the rank of the odd one is, the rank of the odd one is exactly the order of vanishing of the Dedekind zeta function associated to this number field at 1 minus n. This is a big theorem of Armand-Borel. Okay. Now, how does this tie to what you know? Well, let's look at the lower ones at K0 and K1. Remember, in this line over here, I only looked at n greater than or equal to 1. So I'm not capturing K0 and I'm not capturing K1. Well, K0 is more or less the ideal class group. So it's the ideal class group of OKS plus a copy of Z. Okay. And K1 is exactly the group of S units. And you know that the rank of this K1, the rank of the group of S units, is the order of vanishing of the zeta function at S equals 0. Yeah. So what I said before about the higher ones is nothing else but what happens at S equals 0 with this classical invariance, the ideal class group, which is more or less K0, and the group of units, which is more or less K1. And as you know, Dirichlet's class number formula, which was in fact proved by Dedekind that S equals 0, because Dirichlet could not, definitely not Dirichlet, not even Dedekind, it was proved by Hecke at S equals 0, because Dedekind could not continue his function to S equals 0. So this class number formula relates the special value, the special value of the Dedekind zeta function at 0 to K0 and K1. K1 shows up via a regulator, K0 shows up via the order of this ideal class group, which is more or less K0. Yeah. So there are precise links due to Borel and Lichtenbaum. Borel made these links rational up to rational, non-zero rational factors, and Lichtenbaum made them more precise in the 1970s between the leading term of this zeta function at 1 minus n and the higher k groups, k sub to n minus 1 of OKS, k sub to n minus 2 of OKS. So the order of the even one shows up, that's like the class number. And there is a Borel regulator, which tells you about the free part of k sub to n minus 1. Okay, so the class number looks, the leading term formula looks pretty much like the classical class number formula, except for the fact that you replace units by k sub to n minus 1, and you replace the ideal class group by k sub to n minus 2. Okay, by the way, we have no idea how to prove Lichtenbaum's conjectures in general. So these class number formulas are conjectured, but we cannot prove them in general. We can prove them, for example, if capital K is an abelian extension of Q. Okay. This is work done in the 80s, late 80s, early 90s. Okay. So what does the conjecture of cotes and synods say? Well, it says something like the Brumer-Stark conjecture. So you take this theta, at 1 minus n. You are not looking at it at 0. So now I'm taking n to be greater than or equal to 2. You have to smooth it out. It's not integral, it's rational. We've known this since Klingon and Siegel. How do you smooth it out? You hit it with the annihilator over Z bracket G of the torsion piece of the odd K group. Okay. That is like hitting theta at 0 with the annihilator of the roots of unity. That's the torsion piece of K1. Okay. So, and you are supposed to end up in the annihilator of k sub to n minus 1 of OKS. So this is the higher analog of the ideal class group. And so here is what we prove. So we prove something stronger. This was also proved by Nickel and Johnston as a consequence of their version of the equivariant main conjecture. And so we simply showed exactly what I announced, that the fitting ideal of so replace here the annihilator by the fitting ideal. This is not big deal because in fact, this turns out to be cyclic. so fitting and annihilator are the same, times theta, yeah, times this value, it's in fact a piece of the fitting ideal. So clearly inside the annihilator, no doubt about it, it's a piece of the fitting ideal of the even K group, okay, times this En for all n greater than or equal to 2. So this is strong code SYNET, unconditional now. I mean, we are not assuming mu equals 0. This was the condition that, I mean, the hypothesis that Greiter and I were working under. So we are not assuming that anymore because the equivariant main conjecture in Iwasawa theory is proved unconditionally. And now, so I'm not going to show you the proof, but I want to show you, I mean, how in the world do K groups show up in this picture? I mean, you only saw K groups in the previous slide, not in one of the slides before that. I mean, the equivariant main conjecture has nothing to do with K groups. Well, there is a big result here that we are taking advantage of. So this is an isomorphism, a canonical isomorphism between K sub 2n minus I, so the 2n minus I K group, tensored with ZP, the P primary part, and a certain étale cohomology group, HI étale of OKS with coefficients in ZP of n. And this happens for all I in between 1 and equal to 1 or 2, yeah? So H1 and K sub 2n minus 1, and H2 and K sub 2n minus 2, and for all n greater than or equal to 2, okay? This isomorphism was conjectured by Quillen and Lichtenbaum. This was known as the Quillen-Lichtenbaum conjecture. So this is the transition between Quillen K theory and étale cohomology. The maps themselves are canonical. So these are the so-called p-adic Chern character maps, and they were constructed by Soulé and by Dwyer and Friedlander. And they were known to be surjective for p greater than 2. One more time, p equals 2 is very different. Yeah, and Rost and Voevodsky proved that they are isomorphisms, as conjectured by Quillen and Lichtenbaum. Okay, so this is the transition between K theory and étale cohomology. Now, if you have étale cohomology, you know that Iwasawa theory, the way I presented it to you, is about étale cohomology. Okay, so what is the exact link? The exact link between our modules, the Zellmer modules at the top of the Iwasawa tower, and the étale cohomology groups that are relevant in this isomorphism is the following. So if you want to get H2 et al., this one, H2 et al., then that is nothing else but Zellmer twisted a la Tate n-1 times, gamma coinvariant, so you do co-descent down the Iwasawa tower, and then you take the Pontryagin dual. It's an isomorphism. We are proving that. It's not very hard to prove. Once you have this link, I mean, with between K groups and étale cohomology groups, you forget about K theory, you take into account étale cohomology, and you want to relate it to these Iwasawa modules. And the same thing happens to H1 et al. I mean, this has nothing to do with the Zellmer groups. That's simply ZP of n twisted gamma coinvariant. Okay. Once you have that, then you know, the main conjecture tells you something about theta at 0, but in fact, the main conjecture, the equivariant main conjecture plus a p-adic interpolation tells you about theta at 1 minus n. So if theta at 0 is in the fitting ideal of the Zellmer group, theta at 1 minus n turns out to be in the fitting ideal of the Zellmer group twisted by n minus n, a la Tate. Taking values of the L function at negative integers corresponds at the level of Iwasawa modules to taking Tate twists. That's all I'm saying here. And so now you see the strategy. I mean, so you know this, the fitting ideal of the Zellmer group, you know the fitting ideal of the twisted Zellmer group. You do co-descent, you are recovering the special values at negative integers of the classical L functions, of the classical equivariant L functions. at the finite level. And that's how you do it. I mean, there is a homological algebra argument here, which is quite complicated. So this is the technique I designed with Greiter, not for these Zellmer groups, but for the Picard-1 motives, but the same technique works here, and you obtain the result as stated. Okay, so I'm running out of time. I'll take one more minute to say that the two primary part of code synod is also proved now. Again, you don't end up in the fitting ideal of the K group. You end up in the annihilator for the two primary part. There are various reasons, subtle reasons for that. And now the question is, so this was never discussed here. Okay, so you know the fitting ideal of the ideal class group. So this is what Brumer-Stark gives you, or Burns-Kurihara-san will give you. How about the higher fitting ideals? Okay, so there is a fit 1, fit 2, there is a fitting filtration. And now we have results on the higher fitting ideals for these K groups. So this is my student's weigh-in's PhD thesis. He just defended it. The paper will be out by the end of the summer. So there are results on the higher fitting ideals of these Quill and K groups in terms of special values of L functions. And now people were talking about motives and moving things from GM to other motives. So I'm excited to say that I moved way away from GM lately, I mean, in the past 4 years. So I've been looking at special values of L functions associated to T motives. These are, so T motives are vast generalizations of Drinfeld modules. And the motive itself, if you view it as a family of representations, Galois, representations of the absolute Galois group, which are compatible in some sense, so you can construct an L function out of the family. The representations in that situation are characteristic P representations. So the L functions take values in characteristic P. It's a completely different world. So I'm happy to say that we formulated the TTNC and proved it in that generality for all T motives, abelian T motives. Otherwise, you cannot write down an L function. And we proved Brumer-Stark and strong code synod conjectures. Had to formulate them and prove them. They are consequences of the ETNC that we proved in that situation. That's work of mine with postdocs and former students, Ferrara, Green, Higgins, and yeah, myself. Ferrara was a student of, as a matter of fact, of Samit Dasgupta's. And Green was a student of Matt Papanikolaou. He was the only expert in Drinfeld modules in that group when we started 4 or 5 years ago. We don't have an Iwasawa theory there. So there are invariants like the ideal class group. They are called Tellman class groups, but we don't have an Iwasawa theory. We are working on it. I'm working on it with various people. Zach Higgins, Nanda Gopal Ramachandran, who is here, and Shev Wu, students. But that Iwasawa theory is non-Noetherian. The Iwasawa algebra is isomorphic as a topological group with a product of countably many copies of ZP. So you are now working over ZP bracket X, the usual lambda ring. You are working over ZP double bracket X1, X2, blah, blah, countably many variables. Things are complicated. You can have finitely generated modules which are not finitely presented. So we are developing the theory. It's not there yet, but it will be soon. We must know, we shall know, as Hilbert put it. Okay, well, thank you very much. Before you clap, so I would like to thank the organizers. Ari, thank you for organizing this conference. And I would have liked to thank the staff of the ICMS for being so welcoming and kind to us. So, and thank you to all of you for staying until the very last lecture.
Oh, if I can add a word, yes, I think that